Good day, everybody. In this presentation, I will try to walk you through the work we done in the topic or in the field of detection of maneuvers from synthetic observation of satellites. So the structure of the presentation is as follows. First, I will try to briefly motivate why it is interesting and necessary to detect maneuvers of satellites. Then I very briefly mention some previous works in this area or this field. And then the center of gravity of this work is a generation of synthetic dataset for the maneuvering satellites. This bit will be a bit heavy on physics, but do not get discouraged. I will try to skim over the physics part, and then I will talk about some results regarding the detection of maneuvers with machine learning and some future direction or future steps. So the reason why people are interested in detecting maneuvers, well, one of them can be seen in this graph, which shows the growth of the artificial objects in the orbit of our planet. And as you can see, the growth starts to, I would say, grow exponentially, which is mainly due to presence of the debris, which is fragmenting and congesting the orbits. So the reason why we need to detect maneuvers is to have an awareness, which is necessary for the people that are operating, awareness of the other objects and what they are doing, which is necessary for the people that are operating maneuvers. It is very necessary for the catalog keeping, where this can cause some numerical instabilities in some routines if we don't know that there was maneuver. It's necessary for future mission planning, the fuel allocation, and etc. And in recent years, it also became necessary to detect the maneuvers because of malicious activities by other governments. So there are some, I would even say, military reasons to this. Then we have some other hypotheses regarding the maneuver detection, as we believe that some maneuvers, which are not a result of a station keeping or regular maneuvers, which are performed by operators, could be indication of faults. So for example, if you have a rocket, which you know that is inactive, it's a piece of debris, which is non-maneuverable, and there is something going on, which looks like maneuver, this is probably indication that there is some gas leakage or something, and we think, this can precede the fragmentation of that object, which produces debris. So, some previous work. So people were detecting maneuvers on time series of two-element line data. These two-element line data are sort of unphysical data. So if you have an orbit in space, it looks like this. And it looks like the ideal case, without perturbation, the influence of sun and moon, will look like a blue line, which is classical Keplerian orbit, which you can characterize by semi-major axis, eccentricity, and some other parameters. In reality, because there is a sun, there is a moon, the Earth is not a perfect sphere, so the orbit looks like black line, and that is called an osculating orbit. What you have in TLE elements, which are the dataset that is available online, is the red line, which is sort of a mean orbit. But the way they calculate the mean orbit is a military secret, and all I can say that this doesn't correspond to any physical orbit. But from this basically red data, the people try to, for example, methods like this, where you have leading and trailing window and you are fitting semi-major axis, one of these parameters for differences, and then you extrapolate a midpoint, and if this difference is too large, you tag it as a maneuver. But as you can see here, there is a lot of noise in this data, and it's not a perfect. Then people try some other methods, all of them unsupervised because there is not a large enough data set of labeled data. And It works to an extent, but it is not a perfect, and it is definitely not sufficient. We also try to improve some methods in this area. We propose a LSTM-based autoencoder network, which was trying to identify anomalous segments or anomalous sequences. We did have some encouraging results with this, but the approach is not really well scalable, and I would say it's dependent on feature engineering and also some parameter selection. So it's really not well scalable, and that's why we decided to generate a large-scale synthetic dataset of maneuvering satellites for which we would have detailed labels. And because we also decided to use it for some other things, just than maneuver detection from TLE data. And I will walk you through pipeline how physicists observe satellites. So first they took images of sky. They measure right ascension and declination, which are basically two angles that are telling you where the satellite is. From this, they run something that is called orbit determination to produce state vectors. This is basically position and velocity, and position and velocity can be also expressed as the orbital parameter, semi-major axis, eccentricity, and etc. And these observations are highly irregular, so you need to resample them, and then you can detect maneuvers. So our synthetic pipeline starts with basically resampled state vectors. So we simulate those. We have a time series of state vectors that describe the position or the state of the satellite. From this, we can use masking to simulate synthetic observations, and we can go all the way back to right ascension and declination and even to images. Since the orbit determination is rather well-tuned process, we do not want to go all the way to images, so we just go to right ascension and declination and the synthetic observation. From these synthetic state vectors, we can also, in theory, calculate the mean elements. That was the red curve I was talking about. It is a bit tricky because, as I said, the process of calculation, this step is not publicly known, but you can use some NASA software to guess the correct values. So this is the outline of what we are trying to do. And then just very briefly, so the dataset simulation, as I said, we mainly focused on geostationary satellites. Those are satellites that are basically 35 kilometers away from our 35,000 kilometers away from our planet. And the reason why we focus on this area is because it has basically a small variety of station keeping regimes. So the way people maneuver satellites in this area, there are like 2 or 4 approaches, so it's not so hard to simulate. Regarding the propagator, we incorporated the sun pressure, the fact that Earth is not a perfect sphere, so the gravitational field is not perfectly round. We also incorporated sun and moon, and first we implemented our own propagator, but since that was in Python, it was very slow. We swapped that from a high precision propagator from NASA. And the maneuvers are simulated as impulsive burn. So basically, if the satellite fires a thruster, in reality, it is a change in velocity over some time, like from half an hour to few hours. We simulated that as an instantaneous change in velocity. So that is one major simplification we are doing. those are some like special parameters people use to describe the orbit in this regime. I will not try to bother you with it too much. Here you can see that this is the evolution of some of the parameters I was talking about under the influence of perturbations. So if you had a perfect, or if you had only the Keplerian physics without the perturbation, all these would be basically straight lines. But as you can see, they have a periodic variation and some long-term variations which are caused by those other effects.
But those are observations or
those are computed values. All of them are computed values. So the two main things you have to correct for geostationary satellite is a drift in inclination, and basically the strategy is rather easy. You can use one of those fancy elements I skipped over, and basically their evolution is they are evolving like this under the effect of perturbation. And since you want to keep an inclination confined to some range of values, we are trying to confine it, for example, to size that is characterized by this dashed circle. So the station keeping strategy is to get inclination from one end to another, so it can evolve in the circle as long as possible without maneuvers. So you are trying to correct for this, and here you can see simulated evolution with some maneuvers. So you go all the way back to utilize the allocated window as much as possible. Then there is a similar procedure with semi-major axis, where also the evolution is in the parameters that are changed, basically the semi-major axis and the drift rate. It's kind of like horseshoe like this. So you are going from one end of the horseshoe to the other. So the satellite can stay in that band as long as possible, or the allocated band as long as possible. So the inclination is corrected by north-south maneuver, which is maneuver perpendicular to the plane of movement, while the east-west maneuver is corrected by tangential burns. While the tangential burns mainly correct the semi-major axis, there is also different kind of change in eccentricity, and this you can achieve with carefully positioning the location of these east-west burns to get a parasitic effect and change the eccentricity to also keep it in some allocated dead band. What you can see here in this nice picture that is showing you how the inclination evolves over a very, very long period. Sorry, not inclination, eccentricity. I think this one has a period of 57 years. So within 57 years, it does a circle like this. Of course, we are doing the correction weekly, so we are just correcting for the short-term drift, not the long-term periods. Okay, so the physics is mainly done here. So what we are simulating in our dataset are the north-south maneuver, east-west maneuvers. Then we also are simulating the relocation maneuvers when satellite goes from one place about our planet to a different place. And we also are simulating graveyard maneuvers. So that basically at the end of the lifetime of the satellite, you should use your leftover fuel to get satellite out of the geostationary orbit, so it is not causing some problems in there. We did the simulation for many different satellites. There was so the parameters of the satellites are mass, the cross section of the solar panels, the reflection coefficient, and also the location where it originally started. So we, of course, simulated over a range of these values, and every satellite was simulated for 1 year. And here you can see some results, which again shows the parameters that we use to describe the axis, the orbit. So here you can see the semi-major axis, the eccentricity, and the inclination. The red lines are denoting the location of the burns or the maneuvers. As you can see, it's often the change is associated with change in the a bit abrupt like change of the given parameter. So there are still some things missing. So sometimes people discontinue the north-south strategy and they stop caring about inclination to save some fuel. We did not implement this. There is about 4 special places in the orbit where, actually only two special places in the geostationary orbit, and there the geopotential is unstable. So the behavior is a bit different than everywhere else. From when I checked, there are only like 2 or 3 real satellites in these points, and they are somewhere above Atlantic and Pacific. So we omitted this part, and then we did, because we are using, as I said, the instantaneous maneuvers, we are not simulating the electric propulsion, which is like very slow change in velocity over longer time periods. To generate the observation, we take the full time series and we use masking to kind of simulate what the physicists observe. The masking is done in such a way that basically, so if you just want a right ascension and declination, you have to select the data points that are in a window that corresponds to a night. And basically, because the physicists are doing the observation from some observatory, so you also have to take in account the altitude, the sunset times, and whether the satellite is above horizon or below horizon. And there is also like often a technical downtime which we do not simulate because that would only corrupt data set. So regarding the maneuver detection, so first we took the full time series without the masking. So basically what we simulated, it has 72 data points per day. So basically there is data point every 20 minutes. And we use a simple CNN inception based network, with which we achieved the F1 score of 0.97, which is rather, I would say, good, and it even outperformed some of the previous things I've seen that people got to 0.93, I think. So that's fine. But then we moved to the mask time series. So the masking is rather strong. So from why originally we had 72 data points per day, now we are ending with something between 3 to 6 data points per day. So the large majority of the samples is removed. Also because the label of the original maneuver can be in a mask segment, for example, the local day, we are shifting the label of maneuver to the next observation because we do not, because yes, it would be totally okay to predict maneuver anywhere in the mask segment. So we are shifting maneuvers to simplify. And here you can see, for example, semi-major axis of one particular satellite. The blue line is the full or the original simulated trajectory or the simulated semi-major axis. The red dots are denoting the masking, and the vertical lines are denoting the maneuvers. So in this case, the red line is east-west maneuver, which is exhibiting in behavior of the semi-major axis, while north-south maneuvers are not affecting the semi-major axis. They are manifesting in some other parameters such as inclination. Here the case is a bit more tricky. Here we simulated dual burn. So there is only single burn in east-west maneuver. Here we are simulating dual burn, which is better if you want to correct for eccentricity, but it is a bit more tricky to detect. And well, this looks like, well, yes, the time series is periodic. It is not easy to detect maneuvers, especially if you use the aggressive masking. But so for example here, it's similar picture, but here you have only the observations. So you already see that the picture kind of breaks down, and it's much more tricky to detect change if you see something like this. And this is a especially tricky case because, as you can see, the changes in the behavior are rather small. So now we have also the other maneuvers which are not present in the semi-major axis. They can be visible in inclination. Often the change can be very small and hard to detect on masked segment. So I will be honest, I tried many models, I tried many different approaches. Over the summer I trained like 20 or 30 different models. I had some luck with only one, and it is a very weird model. So I cannot give you a very good justification for this model, but I had this idea that when I looked at the original inception network, it was often flagging, if there was a large gap between the observation, it was flagging it as a maneuver, which is not the behavior that I wanted. So I want somehow to incorporate the fact that there is a large difference, or the large elapsed time between the observations. So I use something like an attention mechanism. So basically, you take the original data, for example, semi-major axis, and the input time expressed as elapsed time between the observation. And this is only looking at the observed data points. I dropped all of the masked ones. And then it goes to basically several branches. One branch is basically only working on time. The another branch is only looking at the observed data. And then they are multiplied as in sort of an attention mechanism. Yes, so this is just that we have a convolution of different kernels, so we get a different resolution, and then we concatenate or add. We can choose. I tried both of them to result vector. So this is sort of a time-weighted inception block, and then I have a network which has several blocks of these and some other linear layers to encode the input and output features. And with that, I get a F1 score of 0.89, which is the best I was able to get. To be honest, I still haven't managed to test this on validation dataset. So obviously I split my dataset, but to validate it properly, I'm simulating a bit of a new dataset to see if the behavior can be generalized to completely new set of trajectories. This is still not yet finished, but this is the best I was able to do. And then I tried this on real data that I got from DLR, which is a German aerospace center where I spent an internship in the last spring. And as you can see, the model didn't work because the real data looks like this. This is supposed to be semi-major axis. So this is supposed to be same as this one, or at least this one, which are the observation. It doesn't look like it. So the theory we have, and right now I'm in process of verification, is that you can see here these spikes. And these spikes, I believe, are the result of the orbit determination. So physicists look at the sky, they measure, I don't know, 4 or 7 data points, which are the angles, and then they run some algorithm on this. However, and I found like one article that was basically saying that this is true. If there is maneuver in this observed segment, it will lead to numerical instability in convergence of the algorithm, which produces this spike. So probably to really simulate what they see is I would have to take these right ascension and declination values, which I can simulate, which I have, and then I cannot take the, let's say, like the real position and real velocity that I simulated, but I have to calculate this real position and real velocity from the synthetic observation. So I kind of have to insert the numerical instabilities of that orbit determination into this process. I discovered this like very, very lately, like last week. So I'm still not sure if what I'm saying is true, but this is the theory I have.
But do they have any explanation? I mean,
so I told to them, they say they took data from me, they said that they will run an orbit determination on it. They were kind of surprised, we were not expecting this behavior. They were also not, they said that it makes sense, but they weren't aware of the numerical instabilities. So I don't know, I'm still waiting to hear from them. So we will see. So the next steps. So I am in process of constructing a very simple baseline which I could better interpret. That's one thing. Then the orbit determination I was talking about, that's something that probably we need to verify. And then this can be obviously extended. Like one of the approaches how to overcome the observation and the aggressive sampling is again to use the physics-based propagator. But for that you need to correctly estimate the parameters of the satellite. So basically the mass, the cross-section and the reflectance, and you need to estimate that again from the mass observation in order for the propagator to behave nicely. So that's one of the something we can do. And yes, what would be very helpful then to take these simulated trajectories and convert into the TLE data, which are the red lines from the beginning. So basically the mean orbit, because the people are usually looking at this data and there is no labeled data set. Well, there is one, it has only 14 trajectories and that's it. So if we can extend our data set into TLE, that will be very beneficial and very helpful to improve the maneuver detection approaches in this area. And then what's apparently interesting for people that are working on doing the observation would be to give them information that now you should expect that there should be maneuver happening. So for example, in our orbit determination and in some other routines we run on our observation, we should be careful that there was something that happened. So to sum up, in this presentation I explained why we are looking and why we are trying to detect maneuvers. Then I talked about how we simulated the high precision data set of maneuvering satellites in geostationary regime. I went over some models I used for maneuver detection, and then I outlined some possible direction we can take. So thank you very much.